Okay, so for our topic, we have other differentiation rules. All right, so let's start with the first theorem, the derivatives of the other trigonometric functions. We have here for the tangent, secant, cotangent, and cosecant. Now, to apply these derivatives, let's look into some examples. All right, so first example we have here function 1 minus cos x over sine x. In the previous lesson, we have used quotient rule for this one, but actually we can use theorems to find the derivatives of this given function. But first, we have to rewrite first the function, like we distribute the denominator. So we have f of x is equal to 1 over sine x minus cos x over sine x. Now, 1 over sine x is equivalent to secant x, while cos x over sine x is equivalent to cotangent x. So this is just rewriting the function. Now, if we get the derivative of this one, so we have the f prime of x is the derivative of secant. So the derivative of the secant, we have this one. Okay, so we write secant x tangent x minus, next is we have the derivative of cotangent. So we have this one. Okay, so minus negative cosecant squared x. And then simplifying this one. So we have now secant x tangent x plus cosecant squared x. And that's it for our first example. Okay, now let's proceed to second example. This time we have secant x cotangent squared x. So in this case, we have the theorem for secant, yes, but we don't have the theorem for cotangent squared, right? Cotangent squared. So it would be much easier to rewrite the function. So let's try to express all the function in terms of sine and cosine. So let's see if we can simplify something. Okay, so we have here the function f of x is equal to secant is 1 over cos x. Okay, and then secotangent is cos x over sine x. Since it's squared, so duha. So you have cos x over sine x. And if we look at that one, we can actually cancel, no, 1 cosecant. So what's left is we have 1 over sine x and times cos x over sine x. Okay, and we know that 1 over sine is cosecant times cosecant over quan is cotangent x. With this, we can make use, no? We have cosecant here, so we can use this. Then we have cot here, so we can use this one. But since it's a product of two, then we will employ product rule, okay, when we get the derivative of this function. So let me write, okay. So when we get the derivative of this function, then we use the product rule. So we have f prime of x is equal to u v prime plus v u prime. All right. So u is, you have cosecant x times the derivative of your v prime, so cotangent, so this would be, no? So we have here negative cosecant squared x plus the v is cotangent x times the derivative of your u is cosecant, so we use this one. Okay, so times negative cosecant x cotangent x. And so we try to simplify. So we have here, that's negative cosecant cube x. And also here, no, we multiply. Then we have negative cosecant x cotangent squared x. And yeah, that's it. No, there's nothing to combine or simplify. Okay, next for our second theorem, we have here the derivatives of natural logarithmic functions. So these are logarithmic, but since it's natural, the base is e. Okay, so in here, no, you can find ln of x. Okay, so when you get the derivative of in the form of ln x, no, you have 1 over x given that your x is greater than 0. It cannot be negative. Okay, so it should be greater than 0. However, if it's not x, what if this is like x plus 1? The one. So we have here the second one. No, if it's a function in x, no, like your u is equivalent to x squared plus 1, like that. So what you do is, same with this, 1 over x, but this time is 1 over u, but you still have to multiply it to the derivative of your u. In short, it's u prime over u. So you just have to define your u. Okay, so it's u prime over u, given that your u is greater than 0. So let's have some example to illustrate this theorem. Okay, so here we have the function equals to ln 2x. Now this 2x here is, it's not x, no, it's not this l, so we cannot use this one because it's not x, it's 2x here, 2x. So in that case, we use this one, no, u. So our u here, no, is the 2x. No? Our u is equivalent to 2x. Okay, so the u prime would be the derivative of 2x. So the derivative of 2x is 2. Alright, so it would much be easier to use the formula. So when we get the derivative of our function, so we get the f prime of our given function. So we use this formula here, this one, okay, u prime over u. So yeah, I'll just write that one, u prime over u. So we have u prime is 2 over u, 2x. Okay, and then we cancel this. So in that case, your f prime of x is equal to 1 over x. And that's it. Alright, so let's have another example. So this time, our u here is a 5x minus 3. Okay, so that's your u. No, this is your u. Right? So your u is now equal to 5x minus 3. So when you get the derivative, so that's your u prime, derivative of 5x minus 3 is 5. Okay, so if you apply the formula here, this one, okay, so we have, okay, f prime of x is equal to, that's u prime over u. Okay, so that would be u 5 over 5x minus 3. And that's it. Okay. Alright, so for our third theorem, we have the derivatives of natural exponential functions. So these are the inverse of the natural logarithmic functions. You have the base e. Okay, but this time it's exponential. So here, let's look at the theorems, no? So when you get the derivative of a function in the form of e to the x, the derivative is just e to the x, meaning there will be no changes. Okay, so, but what if your x here is not x? It would be a function in terms of x. So it's u. So when you get the derivative of in this form, so you have to use this formula. So the derivative of e to the x is just u is e to the u, but you still have to get the derivative of the u. So it's like the derivative of e to the u is equal to e to the u times u prime. All right, so let's have some examples like this one. All right, so for this one, this is a constant, right? So if it's constant, we simply set it aside and then get the derivative of the remaining with variables. So in this case, so f prime of x is equals to 5 times what's the derivative of e to the x, and that would be e to the x, right? So derivative for this one is 5 e to the x, and that's it. So let's have another one like this one. So in here, in this example, the exponent of your e is in the form of a function which is 3x squared minus 2. So this is your u. Okay, so let's write that one. It's 3x squared minus 2. And then let's determine the u prime, so we could easily use the formula. Alright, so the derivative of that would be 6x. Okay, so to get the derivatives, we'll use this one. No, it's e to the u times u prime. Okay, so we have f prime of x is equal to e to the u, and that would be e to the 3x squared minus 2, right, times, or yeah, let's use parentheses, times the u prime, or the du dx, okay? Take note, this is also du dx. Okay, so that would be 6x. And just rewrite that one. Okay, so f prime of x is equal to 6x e to the 3x squared minus 2. And that's it. Okay, now for our third theorem, we have the derivatives of bases other than e. So we have here the exponential and the logarithmic, where the base is not e. Okay, so here for the exponential, with any bases, as long as it's a positive real number, then we have here, no, if it's a raised to the x, like 3 to the x, or you could have 2 to the x, as long as it's a number here, it's not letter e, no, tapos the variable is in the exponent, then it's an exponential form in this manner. Okay, so you have, when you get the derivative of that, you have ln of a times a to the x. But you have to be careful that you have to write it within the parentheses. But you can also rewrite this one without the parentheses, ax ln of a. So in this case, they are clearly separated. Now, however, what if your exponent ng x is a function? So we have here the second option. You let it as u, no? And then you write the same manner as this, but this time it's ln of a times a to the u. But then you still have to get, multiply it by the derivative of your u. Or other way of writing this one, you could have a u ln of a times u prime. U prime. Okay, so that's for the exponential. Now for the logarithmic, so the base here is a number, so it could be like in the form like log of x at the base of 2, like that. So when you get the derivative of that, then it's in the form of 1 over ln of a times x, or you can write it as x ln of a. Okay, Now, what if your x, no, your x here is a function like x plus 1, like x squared minus 3, like that. So, we let that as our u, no? So, similar, but this time you still have to multiply it with the derivative of our u. Okay, so we can also rewrite this one as 1 over u ln of a times u prime, no? Or you can write it in the numerator. Okay, you can have u prime over u ln of a. Now, so let's have some examples to see how we use these theorems. Okay, so example here, you have f of x is equal to 2 to the x. So in that case, it's a base is a number, no? So 2, and then the exponent is just x. So in that case, we can use this one, no? It's just a to the x. Okay, much like this one's your a, no? And then x. So much like a to the x form. So in that case, we will use this formula, no, to get the derivative of this given. So you have f prime of x is equal to a to the x. So your a is 2. So 2 to the x ln of 2. And that's it. Okay. So let's have our next example, number 8. So this time it's 3 to the 5x minus 4. So if you notice, it's in exponential form with a base 3. So this is your a. But this time, our exponent is a function, so we have a u, right? So you can also write, no, your a is equal to 3, and then your u is equal to 5x minus 4, and then your u prime, because we need the u prime, is 5, no? Because in this case, we will employ, or we will use this formula. Okay, so we have the f, so we have the f prime of x is equal to, no, a to the u, so you have 3 to the 5x minus 4 times ln of a. So ln of 3 times the derivative of your u, which is 5. So in that case, you have 5 ln of 3 times 3 to the 5x minus 4. This will be your final answer. Alright, so next example is on logarithm, but this time you have log of x with base 4. Now, you have here your base, this is your a, and then we have the x. So in that case, we use this formula to find the derivative. So your a, so your a here is equal to 4. Okay, so when we get the derivative, f prime of x is equal to that's 1 over x ln of a, so that would mean 1 over x ln of 4. Okay, so rewriting that one, we have 1 over x ln of 4. Alright, so for our last example, the log of 2x cubed plus 1 with base 7. Okay, so in this case, our a, again, this is our a, and this is our u. Okay, so our a is equal to 7, our u is equal to 2x cubed plus 1, and our u prime is equal to 6x squared. Okay, so we will utilize this formula here, that one. So f prime of x is equal to, I'll just rewrite the, you have u prime over u ln of a, right? That's the formula. So u prime, we have 6x squared over u which is 2x cubed plus 1. Put it inside the parentheses, and then you have ln of 7. Okay. That's it. And that's the end of this lesson.